And we are ready to get started with today's episode of our Demystifying Industrial AI webinar series. Just a reminder that this is a multi-part series. So the first part from last month, From Mainstream Approaches to State of the Art, that's available now on demand. We'll provide a link to get that on-demand webinar at the end of today's session. Part 2 today, we're talking about from first principles to foundation neural networks. And then part 3 will be coming on January 8th, and that is a taxonomy of process control and optimization. Foundation neural networks and reinforcement learning through traditional kind of approaches. Just a few housekeeping reminders for today's webinar. So this event is being recorded. That recording will be emailed to you. If you have questions at any time during the webinar, we invite you to submit them using the questions console on the bottom right of your Livestorm application. So this is different from the chat. So please use the chat for any kind of logistical questions if you can't hear or anything, but for actual Q&A that you'd like Nadav to answer, please use the questions console, and that live Q&A will be following his presentation. Throughout the session, we will use polls to potentially ask you questions. And so we're going to start off the day with a quick poll just to gauge who's in the audience and what roles we've got here today. So you should see a poll pop up now. So we'd love to know what part of your organization you're coming from today. And if your role isn't listed specifically out here, just throw the name of your role in the chat so we can kind of tailor the discussion today to the different roles we've got present. All right, we've got a battle right now between the process control engineers and the process engineers, looking at about half of each, a couple folks from data science, some folks for other. So I hope you guys have thrown your titles in the chat so that Nadav can see. All right, it looks like we're shaking out with about 40% process controls, APC or RTO engineers, followed by process engineering, and then the AI and data science folks. So thank you for participating in that. And now with that, we'll go ahead and get started with today's session. So I'm going to hand it over to Nadav Cohen at this point.
Thank you very much, Allison. Let's just confirm that everybody can hear me.
Correct.
Okay, great. So thanks everybody for joining. As Allison said, this is part 2 of our Demystifying Industrial AI series. And today we will talk about the journey from first principles to foundation neural networks. We're going to understand what that means. A few words about myself. I am the CTO and president and the co-founder of Immubit. My area of expertise is the mathematical foundations of AI. I'm a professor of computer science. I was fortunate to receive several recognitions for my contributions to the foundations of AI. And alongside the academic background, I have about 2 decades of experience applying AI to different critical industrial systems. And without further ado, let's talk about AI. Right? These days, it really needs no introduction. It's transforming almost any domain, and including the industrial domain. And the outline for today's talk will be as follows. Okay, so when one applies AI, there are 2 aspects that define the regime in which the solution operates. One is the framework that's being used, and there are various types of AI frameworks that are very different in terms of how powerful they are and how complex it is to implement them. On the lower end, there's supervised learning. On the higher end, reinforcement learning, and this is something that we discussed in length in part number 1. The other aspect, the other axis, is the model class that's being used. And here too, there's great variability. Starting from first principles models where not a lot is being learned. It's mostly hard-coded. There might be a few parameters, but not much more. And moving on to foundation neural networks, which we will define. And you can think of different combinations of framework and model class. Okay? And most of the applications in industrial AI and specifically in process manufacturing are on the bottom left corner. And on the top right corner, that is state-of-the-art AI. And the journey that we're going through in the first two parts of the series are from the bottom left corner to the top right corner. And today, we're going to talk about the horizontal part of the journey. We're going to focus on supervised learning and talk about the move from first principles to foundation neural networks. And that is going to complete the picture that we started last time when we talked about the move from supervised learning to reinforcement learning with our focus on foundation neural networks. So a reminder, what is supervised learning? That is a paradigm for designing a model, okay, which for our purposes is some input to output mapping. Okay, so the possible inputs could be time series, maybe of some physical quantity, like temperature, taken on a minute-by-minute basis, and they represent measurements from some unit. And the possible outputs could be one of a finite number of categories, like A, which is red, that could mean that there's a problem. B is green, could mean that everything's good, and C could mean that maybe there's a warning. And a model simply produces an output for a given input. Okay, so you receive a time series and you produce an output. The traditional way to design models is based on first principles and on domain knowledge. You are an expert on your unit, you know how its temperatures are supposed to behave, and you can come up with a set of steps that will conclude with a decision of the category that this input belongs to, okay, whether the unit's doing fine or not. So we, mankind, or the community, we managed to do a lot with first principles models, but it turns out that there are things that are difficult to solve this way. It's difficult to take everything into account. And supervised learning offers a very different approach. Here, instead of handcrafting a model, we learn from examples. Okay, so what does that mean? Instead of taking a specific model, I take a big class of models. Okay, it's usually a parametric family, often basically infinitely large, and I collect training data, which are examples. These are pairs of an input and the corresponding output. So I'm telling my system that if the input is the leftmost series, the output is B. If it's the rightmost, the output is A, and if it's the middle one, then the output is C. Okay, so I collect these examples, and then I feed them into a training engine, which is simply a search for the model in my model class that best agrees with the training data. Okay? Then I take that model and use it in the world. That is supervised learning. Okay? And now let's think of a simple example. Okay? In our example, the input is just a real number, and so is the output, just a real number. And now we're going to consider different types of model classes. The first one is going to be degree 0 polynomials. I will remind what that means. The second, degree 1 polynomials. The third one is going to be degree 2 polynomials. And the fourth one, the last one, is going to be degree 30 polynomials. What is a polynomial? It's a function that looks like this. So a degree n polynomial is a sum of powers of my input is a real number, it's x. I take it to different powers, okay? Power 1, power 2, power 3, up to n, and I have a weighted combination of those. That is a polynomial, and for different coefficients, which are denoted here in the slide by a with a subscript, I get a different polynomial. So for degree 0 polynomials, these are just constants. So if I plot them, they look like this, right? This is a plot. I plot the output versus the input, and I have different possible constants. Degree 1 polynomials, these are linear mappings, more precisely affine mappings, and they would look like straight lines. And I could have different types of linear mappings, okay, like you see here. Degree 2 polynomials, these are parabolas. Okay, so they could look like this, could be like a crying mouth or a smiling mouth. There are various different options. And degree 30 polynomials would be these crazy functions. So these are the types of model classes that we're going to consider in this simple example. Now let's think about the training data. And we're going to consider here two scenarios. One where we have a small data set. Okay, so this is our data set. Every point here corresponds to a pair of an input value and a corresponding output value that the model should produce for that given input. Okay, so if I think of my model as a function and I'm going to plot it, it needs to pass through these points. Okay, so this is scenario number one. Scenario number two is where we have a larger data set. Okay, so we have more points. And now we're going to focus on scenario number one and try to fit the data with the different model classes that we saw in the previous slide. Okay? So if I try to fit the data with a degree 0 polynomial, probably the degree 0 polynomial, the constant that best agrees with the training data, is going to be something like this. And maybe the best degree 1 polynomial, the one that agrees best with the training data, is something like this. And possibly the best degree 2 polynomial is something like this. And the best degree 30 polynomial, one of the best, would be this. And it perfectly matches these points. And now there's a question of which one do we feel is the best model? Which one do we feel captures the true relationships? And most would probably answer the degree 2 polynomials, right? It feels to us like this one captures the true relationship. Degree 0 and degree 1 polynomials are just incapable of capturing this behavior that's non-monotonic, right? The trend goes up and then down. They're incapable of capturing that. The degree 30 polynomial, on the other hand, is capable of capturing that, but it suffers from a different type of error. It perfectly fit the training data, but it did so in a way that doesn't make sense to us. It doesn't seem reasonable that the true relationship is what you have in the purple line here. And so it fit the data, but in a way that doesn't make sense, and that is called overfitting in the machine learning or AI jargon. Now, if we move to the second scenario with a larger data set, now the best fit with degree 0 polynomials, maybe something like this. Best fit with degree 1, something like this. Degree 2, it'll be something like this. And this is the best fit with degree 30. And if I ask now which one is the best, then most would probably say that it's the degree 30. So here, by adding more data, I avoided the overfitting. Okay, and then I could take advantage of the fact that the degree 30 polynomials are rich enough to capture these fine subtleties in the data. Okay, so what we just exemplified here in a very, very simple setting, just polynomials with scalar input, scalar output, that actually is a manifestation of the most fundamental phenomenon in machine learning, in AI. And it's called the bias variance trade-off. What it means is that the quality of the learned model is determined by two factors. One, bias, which corresponds to whether or not the model class is capable even of representing the true relationship. And the other is variance, which corresponds to whether there's overfitting or not. Okay? What I'm going to try to do now is illustrate the bias and variance in a very abstract and general way. So here's an illustration of all the possible models that there are. And within it lies some grand truth optimal model. This is the reality. Now, inside, there's some subset that corresponds to the class of models that we defined. Somewhere in it is the best member of the model class in terms of being close to the grand truth model. Okay, so this is something that exists, but we aren't necessarily able to find it. What we are able to find is the member of the model class that best agrees with the training data. That's what we get when we train. And we care about the quality of this thing, and it's governed by two factors. One is the bias, and it's what you see here. This results from my model class not necessarily being able to represent the grand truth behavior. And the second is variance. how suboptimal is the model that I learned from the data compared to the best one in my class? Okay, did I overfit or not? So the bias variance trade-off tells us that if I expand my model class, I make it bigger, then the bias goes down. That's pretty obvious because I can only represent more. But the variance goes up. I am more prone to overfitting with a larger model class. And I can remedy the situation with data. Okay? If I have more training data, then I decrease the variance. I'm less likely to overfit, just like we saw in the polynomial example. And I don't impact the bias at all because I didn't change my model class at all. Okay? So this is kind of a general framing and illustration of what we saw in the case of polynomials. Now, let's talk about three types of model classes that we will consider today. The first are first principles models. Okay? These are typically models that are fully constructed from scientific laws and equations. They might have some parameters, but usually they don't have a lot of them, and they are built from fundamental equations. Okay? So that's the first model class that we consider. Second one are kind of hybrid models known in the industry, and they are combinations of first principle models with neural networks. So typically it'll be a first principles model where some component of it can be learned with a neural network, which I will remind or explain what that is. So that's model class number 2. And model class number 3 is what we call a foundation neural network. And that means that my entire model, the entire input to output mapping, is realized by a neural network that's typically very large, it's very deep, and it's very wide. Okay? And I'll now briefly talk about what a neural network is and what it means for it to be deep and wide. Okay, so this is kind of a side note. So neural networks, in their broadest definition, is kind of the way I like to think of them. That is a learnable function, a function that I learn, and it is born by composing transformations one on top of the other. Okay? So what does that mean? I have my input, x, okay? This is a time series of temperatures taken on a minute-by-minute basis. I apply to the input some transformation, f theta, so theta is, these are parameters, so it's a parametric transformation, and I get some result. Then I apply to that another transformation, g phi, with phi being parameters. And then I apply another one, hc, with psi being parameters. Then I get my output. So in this case, I applied 3 transformations, one on top of the other, to get my output. Each transformation is parametric. So the learnable functions, every learnable function is defined by a triplet, the 3 transformations. And each transformation is known as a layer. So this would be a 3-layer neural network. And the combination of all the parameters of the layers, that's called the weights, or the parameters of the neural network. Okay, so this is a very abstract and high-level definition. And what I want to do now is give a very concrete and simple example, which actually is being used in real life. Okay, and that would be a feed-forward, fully connected neural network. Okay? In a feed-forward, fully connected neural network, my input is a vector. And then the first transformation is to multiply the vector x by a matrix W0 and adding some vector B0. Okay? So that's an affine transformation. The parameters are W0, the matrix, and B0. It's a vector, and it's known as biases. Okay? W0 are known as weights, weight matrix, and the bias vector. And after this affine transformation, I apply to the result some nonlinear function, sigma. That's called an activation function. And it simply takes a vector and operates on it coordinate by coordinate. It's a nonlinear function. It's important that it be a nonlinear one. And there are various types of activations. The simplest one, which is being used in real life is called ReLU, rectified linear unit. And what it does is something very simple. If the coordinate's positive, it'll leave it as it is. If it's negative, it'll clip it to 0. It's the red plot that you see here. So it's very simple. I applied an affine transformation to my input, and then I just clipped all the negative coordinates to 0. That's it. That's layer number 1. Then I do it again with a different weight matrix and bias vector. That gives me layer number 2. Do it again and again and again. And finally, I just apply an affine transformation, multiply by a matrix, add a bias vector, and I get my output, which is a vector 2. All the layers besides the last are known as hidden layers. Okay? The architectural parameters of this neural network are the input dimension, capital D, the output dimension, capital K, the width of the neural network, that's the dimension of the hidden layers, and the depth of the neural network, which is the number of layers. Okay? The learned parameters are all the weight matrices of the different layers and all the bias vectors of the different layers. And I can count how many parameters there are, and this would be the result. Most of the parameters are in the weight matrices. The size of each weight matrix is roughly m squared, and I have L of those, so it's roughly L times m squared. And the exact formula you see here is not that important. All right, so that was a side note on neural networks, and now let's get back to the 3 types of model classes that we're considering. First principles models, hybrid models, which are a combination of first principles and neural networks, and foundation neural networks, which are deep and wide neural networks that implement the entire model. Okay, so these are the model classes, and now let's consider the bias and the variance when using each of these model classes. Let's start with the variances. Here's a table. We have the 3 model classes, and we're going to consider here 3 regimes in terms of the training data size, the training set size. One is when you have a small data set that, for our purposes, you could think of tens of examples or less. Another is when you have more, like a medium-sized training set, that'd be hundreds to thousands of examples. And another is when you have a large data set, okay, which would be tens of thousands of examples or more. So starting with the first principles model, this is one that has a small number of parameters. So even when you have a small training set, that already could be enough to prevent overfitting. Okay? If you have 2 parameters and you have 10 data points, that's usually more than enough. Obviously, if you have more data, it only helps. You're not going to overfit. When, on the other hand, you look at hybrid models and foundation neural networks, then with a very small data set, it is likely that they will overfit. If you have a large data set, then most likely they won't. And if you're in the middle, then maybe they'll overfit, maybe they won't. And that's kind of roughly the state of affairs. I'm obviously not proving this, but this is something that is conventional wisdom and practice and actually can be backed by certain theories. Now, let's talk about the biases. Okay, so we have the 3 types of model classes, and we're starting with first principles. And what I'm arguing today is that with first principles, usually the bias is high. And what do I mean by that? It's going to be high unless the ground truth model really obeys all the different equations. Now, when you build a first principles model, then obviously there are the scientific laws, which are correct. And that's the problem is not with them. The problem is with all the assumptions that need to be made when constructing a first principles model from these equations. In one way or another, you have to make a lot of assumptions. And while these assumptions are met in some cases, in many cases, especially very complex ones, they're not. And so you end up in a situation where you have a small model class that has a pretty significant bias. And this is not always the case. Sometimes first principles models are very accurate, but in many cases, from our experience on very complex problems, it's very, very difficult to have an accurate first principles model. And the reason is precisely because the assumptions that are required for building that model are often not met in practice. In the case of a hybrid model, and here I'm arguing again that you still need to make a lot of assumptions when you build that first principles model, that those components that are based on the first principles. And unless the ground truth adheres to all of these assumptions, then you're going to get something like this. The model class is a little bit bigger, but still there's a significant bias. So again, there are cases where all the assumptions that are made when building the first principles are valid, but there are also cases, usually the more complex ones, which in some cases are the more valuable problems. And in these cases, it's very, very hard to only rely on accurate assumptions. Okay, so that's the first principles and the hybrid models. And for the foundation neural networks, the question is, what is their bias? Okay. And what we're going to do now is turn to mathematical theories, and starting with a result that's fairly old by now. It's from something like 35 years ago, maybe even a little more. And this result, known as universality, it has different flavors. What it states is something fairly surprising, and that is that a neural network with a single hidden layer, okay, like the fully connected one that we saw, even if it has just one hidden layer, it can basically represent any mapping. Okay, and if I'm a little more accurate, any continuous mapping. All reasonable mappings are continuous. So that simple model that we saw, that simple neural network with just one hidden layer, can already represent any mapping can represent your entire plant, which is kind of amazing. But there is a caveat here, and that is that the width of the neural network may have to be very, very large, okay? Unfeasibly large, like more than the number of atoms in the universe large. Okay, so it's not really a practical result. It doesn't say a whole lot about the kind of neural networks that you can fit in your phone or in your laptop or in a supercomputer. The width that is required is often much higher. A much newer set of results known as depth efficiency, they establish that when you add layers, when you make the neural network deeper, then you can realize functions a lot more efficiently with a much, much smaller width. Okay, deeper networks can be a lot narrower. And this was proven in the last decade. These are some of the early results along this line that I was fortunate to be a part of. And this is when I got a Google doctoral fellowship for. So returning to the picture of biases, with foundation neural networks, if the neural network is deep enough and wide enough, then the bias is going to be low because you can basically represent any reasonable function. And then the situation looks something like this. Right? The class of models is almost as large as the class of all possible models. Okay, almost as large as all the possible models, and therefore it will be able to get very close to the ground truth model. Okay, so summarizing the biases and the variances. So this is the picture that we have with biases. Okay? And this is the picture that we have with variances. And if I want to have low bias and low variance, which will guarantee that I have learned an accurate model, then according to these findings, what I need to do is work with a foundation neural network and have a large data set. And so to overcome the bias variance trade-off, that means learning a high quality model, I need a foundation neural network and I need a large data set. Okay? And this combination actually underlies all of the breakthroughs in AI in the last 15 years or so. That's what I would argue. All of the major breakthroughs are a result of combining large and deep foundation neural networks with large data sets. This includes image recognition, speech recognition, and also all the generative AI models make use of very large data sets and foundation neural networks. And there are various other examples. Okay, so one thing you could ask is, what if I don't have a very large data set? What if my data set isn't always entirely accurate? What if it doesn't cover all the different regimes? Can I somehow cope with this? Okay, can I deal with this? And the answer is that you can, while still using the power of foundation neural networks. And you could do this with what's called guiding first principles. And so what does that mean? Here's the situation that we have with a foundation neural network. It pretty much includes all the possible models, and the bias is very low. And now you have a certain model that fits the training data, but you don't have just one of those, you have a lot of them because the training data isn't that large. And what guiding first principles do is guide the learning to choose the model within those that fit the training data, choose the one that best agrees with predefined first principles. Okay? And these predefined first principles could be things like mass balance, volume swell, different empirical relationships, or more. Okay? And this belongs in general to an area of machine learning known as physics-informed neural networks, and specifically around the type of first principles that you see here. This is actually something that IMUBIT has a patent pending for. So to conclude, in AI, in machine learning, the quality of a learned model is determined by two factors, the bias and the variance. It's always, I think, instructive and easy to go back to the polynomial example. Bias, that refers to the inability of the low degree polynomials to capture the true relationship. Variance, that refers to overfitting, like we saw with the degree 30 polynomial going crazy. In order to overcome the bias variance trade-off, that requires foundation neural networks and large data sets. At least that's how the machine learning community has managed to do it thus far. And that underlies all the state-of-the-art AI systems that I'm aware of. And if you don't have a very high quality and large data set, then first principles can be very, very useful. But rather than building a full-blown first principles model with a lot of assumptions, you can use the first principles to guide the learning. Okay? So that's it for today. And I'm looking forward to your questions and to discussing the next topic in the third and last part of the series. So thank you.
Thank you, Nadav. And for folks who are interested in signing up for the part 3 of the series, you'll see that URL on the slide there. And I'll also ask Maura to throw that in the chat for you so you can sign up for our session on January 8th, where Nadav will deliver part 3 of this 100 level series. So we do have time for some questions, and I see a number of questions in both the questions console and the chat. So Nadav, we'll get started with one on modern AI generally. So are there any specific tasks in the modern AI era in which classic machine learning methods are still outperforming neural networks?
Yes, there are. They're relatively rare. One example is tabular data, where the data is very heterogeneous in terms of the type of features, and there's no structure. You don't know which variables are discrete and which are continuous. There are methods there that work competitively and sometimes even better than neural networks. And that's kind of a known example, but it's relatively rare. Like, neural networks have taken over the vast majority of AI applications.
So continuing this forward-thinking trajectory, we have a question about modern AI models and the fact that they're trained on a huge amount of data. Is there any expectation to see models that are built on an even larger amount of data? Is it even feasible?
Yeah, so the general guideline is the more data you have, the better. And that, by the way, also applies to the size of the model, right? We talked about large foundation neural networks and about large data sets. The, a lot of the ideas behind modern AI were actually around for a long time. And the breakthroughs were driven by our ability to train much larger models because we have much more compute and work with a lot more data because we have the internet and different communication hardware and storage hardware. So the general belief is that the more data, the better. At some point, there could be diminishing returns. In most applications, we're pretty far from it. And so it will depend on the context, whether I believe more data will bring a huge benefit or not. But the general conventional wisdom is that it always helps, at least a little bit.
So switching gears a little bit to the concept of combining first principles and foundation neural networks. The question is, if a hybrid model is made from a combination of first principles with a foundation neural network, wouldn't it be better than just simply a foundation neural network?
Yeah, so that's a great question. And I actually believe it would be better. Now, hybrid is not a well-defined term. You can combine first principles and neural networks in various ways. I gave here, we saw today two different examples. One is that you start with a first principles model, and then you have components inside that are learned by neural networks. And the other, it's kind of the opposite. It's not a first principles first approach, but a data first approach. You take the data that you have, you train a foundation neural network, and then you use the first principles to guide the learning. These are very, very different approaches that lead to very different results. Now, I am not saying that the former approach of starting with first principles is bad. I'm not saying that at all. In fact, if you're working on a problem where you know that all the assumptions you're making actually hold in practice, go ahead and use first principles as much as you can. It's always the best approach if all of your assumptions are valid. But if they are not, then what I am arguing that rather than building a model that is based on assumptions that are violated, from our experience, it's much more effective to use the data to learn and use the first principles, only those in which you're confident, use them to guide the learning. You don't have to build an entire model from first principles that you're not confident in. You only introduce those which you are certain that they are met. Okay, so in our industry, hybrid models usually refers to something specific, which is kind of more of the former approach. But abstractly, hybrid, if you treat it as a combination of neural networks and first principles, then it's a great thing to do. The question is how you combine them. And what I'm arguing is that for very complex problems, a data first approach could be very beneficial. And that's the approach, by the way, that Immubit takes.
So we've got some clearly very knowledgeable folks in the audience that are asking some quite technical questions. So we'll get into some of the methods and the details here. Do you use full cross-validation that keeps aside some samples and use it only for testing and then correct the structure of the model?
Of course, we use validation sets, and that's how you evaluate the models. Well, there are two components to the system. I talked about it last time. One is a learned model of the system, and the other is a controller. So this is kind of, let's focus on the learned model of the system because that's simpler. You want to evaluate how accurate that is. Of course, we leave out data for validation. We also then use data that wasn't even included in training, the most recent data. So of course we do this. I will say, and of course we take different steps to improve the performance on validation. In general, in machine learning, there's a concept of data hygiene. You don't want to overuse your validation set because you could eventually kind of overfit the validation set. But the amount of tuning that we do, especially in terms of the architecture of the neural network and things like that, it's fairly minimal.
So another technical question. We've got a large data set, but with only small variability of the inputs, for example, like a controlled system. Would it be recommended to perform step tests ahead of doing this type of modeling in order to widen the operating envelope?
Yeah, that's a great question. So it really depends. When I say I kind of simplified and I said large data set, I actually meant large data set that captures a lot of variability. Because if I take it to the extreme and I have a large data set of the exact same thing, it's not really large, right? So, so what was just described, it doesn't have a lot of variability. That doesn't really qualify under large data set. Now, this is a place where the guiding first principles could be very, very handy. In some cases, it is also helpful to kind of not step test, but make moves that will enrich the data set. We have in our solution, we call this warm up, where you could have tiny, small movements in the manipulated variables that still revolve around the set point that was defined, and that enriches the data. So at the end of the day, things need to come either from data or from domain knowledge, from first principles. There is no magic here. In practice, it's fairly rare that we require this warm up, and especially step testing, which we never really did. I will say though that even controlled systems, they tend to have a lot more variability than one might think, at least from our experience.
Thanks, Nadav. So I think we've got time for one more question on the air today. And if we don't get to your question, we'll follow up with you individually via email. So the last question of the day is, in terms of deep learning versus foundation neural networks, what are the key differences? And has Immubit's underlying technology regarding these things changed over the years?
Yeah. So foundation neural networks, it's kind of a special case of deep learning. Deep learning refers to the use of neural networks that have more than one hidden layer, have two hidden layers or more. That's the kind of textbook definition of deep learning. The foundation neural networks, these are models that are much, much larger and use a lot of data to train. It's not a technically well-defined term. It's a bit of a soft term. And so you could say that it is the modern state-of-the-art form of deep learning, foundation neural networks. Now, question of has it changed over the years? So a lot, as I said, a lot of the ideas, both around the neural network architecture and the training algorithms, have been around for a long time, decades. And what led to the, I guess, first major breakthrough of deep learning in the modern era, about 10, 12 years ago, was the use of a lot more compute and a lot more data. And so that was something that was not driven by fundamentally new ideas. Since then, there have been some new ideas, both around the architectures and the algorithms. There are different architectures today called transformers or attention models, different techniques for self-supervised learning. I talked about it last time. But if I had to weigh the contribution of algorithms versus data and compute, I would say it's more on the side of data and compute than the algorithms. But there are special cases, especially like around the RL, what I talked about last time, or around ChatGPT. There are some special cases, but most or many of the applications today are still based on the ideas that were around 30 or even 40 years ago.
Well, Nadav, thank you so much for the presentation and for all of your answers to the questions. We've got a highly engaged and highly knowledgeable audience of folks here. And again, if we didn't get to your question online, we will follow up with you via email individually. And thank you all for joining us today. We hope to see you again at the same time on January 8th.
Thank you very much.